today is actually the last lecture of this class. Okay. Um, so we will. I hope to cover up to single value decomposition, SVD. Okay. Uh, because anything beyond that, I think that's a little bit too much. And also, we don't have time to finish one more section anyway. Okay. And in addition to lecture, okay, we will have last quiz today. Okay, and the quiz cover the range quiz covers already announced to you guys some practice questions. So it will be given out in the third class. So I guess the first two classes do not have a lot of students. Maybe that's the reason. Maybe I should switch to start quiz now. If I'm very mean professor, I will do that. Yeah. Unfortunately, I'm not a mean professor. But to be honest, this is actually the last time I teach linear algebra. Okay, because starting from next year, I think I will hand this class over to the new professors. So so maybe at the time when I hand over this class to a new professor, I will tell him or her that maybe a pop-up quiz should be a really pop-up quiz, can be given anytime. 我们还是比较乖的嘛，就是说我跟你讲 quiz， 我都是给你一个固定的时间。其实，在别的学校，在我所知道的像我同学在台科大，有一次我去演讲 ，there's one time, just last week, last Monday, I went there for a speech, and he said, I can have lunch with you, but 1 p.m. I have class. So I said it's a pity. Well, maybe you have a quick lunch and then go to your class. And he suddenly said, one moment, let me arrange a pop-up quiz for my class. And then he stayed until 2 p.m. 所以我那个同学他就突然决定要给他的学生一个 pop-up quiz， 完全没有 no prior announcement. Okay, so I think that's I don't know. Yeah, maybe that's supposed the way it should be, but yeah. Anyway, so back to our class. Okay, so last time we talked about the Hermitian matrix, right? So it's basically it means a conjugate and transpose. Okay, a matrix. If after the conjugate and transpose, it go back to itself, then we say it's a Hermitian. Okay, and then we discuss a couple of properties. Okay, but we didn't have time to finish this section. Okay, so today my goal is very simple. Finish this section, finish the next section. That's it. Okay, that's it. It's a lot of material for this semester already. Okay, although we haven't completely finished this this chapter, but it's really this is the first time I was able to talk about the single variable composition actually. Okay. So first, unitary matrix. The definition, n by n matrix, U is said to be unitary if its column matrix form an orthogonal or the normal set in C. Okay. First, I mean, from here you immediately tell that this is a complex matrix. Okay. At least like you could have like imaginary part in this matrix, right? And also, okay, because its column vectors are orthogonal to each other. So it would be natural, okay, it would be natural, okay, to have U equal to I. Okay, why? Because like when you consider UHU, okay, it's gosh.笨到用油性笔在写这个。到时候下课的时候可以帮我跟楼下借一下那个酒精。OK，因为那个我不知道谁用油性笔写这个没办法擦。We know like this Wij they are this is this column matrix is each of the column matrices are orthogonal. So when you do UH, so it's going to be each of these vectors gets like transpose, okay, into the row vectors, and also they are they become the conjugate of itself. Okay, so then think about this. Your Aij will be the ith row. It will be basically, it will say, let me say, this is a V Hi times the jth column. So that's like the inner product, right? That's the inner product of the complex value vectors, okay? And because these vectors, they are orthogonal. So in other words, this will be delta Ij, okay? Meaning when I and j are different, they are 0. When I and j are the same, they are 1, okay? So it is, so this one is pretty much identity matrix. In other words, UHU equal to I, and since UHU equal to I mean, obviously U inverse is UH. Okay. So having said that, okay, if your unitary matrix, like all the components are real, obviously it will be an orthogonal matrix. Okay, you remember orthogonal matrix means like it's a column vector are orthogonal. Okay, and basically the definition is consistent with what we have here. Okay, because it's just like we don't have an imaginary part, but we're still doing like a transpose, right? And since we do not have imaginary part, so the conjugate part doesn't change anything. So it is still going to be like VIT dot DJ. So that's the real value vectors in the product. Okay, so basically like yeah, that's it. So Corey, if the eigenvalues of a Hermitian matrix A are distinct, then there exists a unitary matrix U that diagonalizes A. Did I finish this? 我们讲过这一页，没有吗？我有讲过这一页，我有点忘记了。啊？六字。啊？对，我说好像unitary没有要考啊。对，但是这一张 slide 有没有教过？这一张 slide 有没有教？忘了。你们有记得？还是你们上次其实没有来？好，没关系。Okay, it's okay. So. If the eigenvalue of a Hermitian matrix A are distinct, okay, then there exists a unitary matrix U that diagonalizes A. Okay. First, okay, we know that different eigenvalue. The eigenvector of different eigenvalue, okay, are orthogonal to each other, right? Previously we have proved that, right? 就是说，如果说两个Okay, if lambda 1 is different from lambda 2, okay, we have this one, right? Right? I mean, like, of course, like x1 is the corresponding eigenvector for lambda 1. x2 is the corresponding eigenvector for lambda 2. Right? So we have this, right? Okay. So how about x1? H x2. We show that. So first, if you apply right? So this is still 0, right? You put the A1, AH on the left hand side. It's still 0, right? Right? So, so A1H AX2, okay? According to the definition for eigenvalue, eigenmagnitude, this part will give us lambda 2x2, right? Right? So we'll have this. Right? Okay. But this one, because A is emission, so this is equivalent to this one, right? Right? Because A is emission, so A and AH are the same, right? So you consider this. So this is right? And then AX1 is lambda 1 plus 1, right? And then, well, lambda 1 is a value, okay? So